Throughout the history of science, individuals have sought to understand how the universe began. The most widely accepted explanation has been what many refer to as the Big Bang Theory, a concept that suggests the universe originated from an extremely dense and hot point. Over time, numerous experts have contributed evidence supporting this idea. However, as science progresses and new technologies emerge, fresh ideas and perspectives challenge long-held assumptions. One such breakthrough comes from the James Webb Space Telescope, JWST, which has captured images of over 750 previously unknown galaxies. These findings are reshaping our understanding of the universe's origins, calling into question the accuracy of the Big Bang Theory. The telescope was designed to help scientists understand how galaxies formed and evolved, but its discoveries have revealed galaxies that are smaller, smoother, older, and more varied than what the Big Bang Theory predicts. According to the theory, galaxies should appear larger the farther away they are as the universe continues to expand. Yet these newly discovered galaxies defy this expectation. The Big Bang Theory posits that the universe began from a tiny super-dense point known as a singularity, which was incredibly hot and composed of all the matter and energy that would later form stars, galaxies, and other cosmic structures. This theory is rooted in Albert Einstein's theory of general relativity. It explains that in the universe's early moments all matter was compressed into an infinitesimally small space, creating an environment of extreme heat and density. For many years, scientists believed this explanation provided the answer to the origin of the universe. However, new data from the JWST is now forcing scientists to reconsider aspects of this theory. The photographs from the JWST challenge the traditional view in several ways. For one, the galaxies it has discovered are older and more diverse than expected. They also appear far smoother than what the theory predicts. According to the Big Bang Theory, galaxies should have visible irregularities resulting from their formation and growth over time, but these observations suggest a different cosmic history. Additionally, the distribution of galaxies discovered by the JWST doesn't align with the predictions of the Big Bang Theory, which anticipated that galaxies would be less abundant in the distant past. The theory also predicted that galaxies would grow through collisions and mergers with the universe's expansion, leading to a chaotic, violent cosmic environment. Yet the images from the JWST show galaxies that are more orderly with fewer signs of disruption or violent collisions. These observations suggest that something about our understanding of how galaxies formed and evolved is incomplete. Challenges to the Big Bang Theory. Despite these challenges, the Big Bang Theory remains well supported by a wealth of evidence. For instance, the redshift in the light from distant galaxies, the distribution of elements like hydrogen, and the cosmic microwave background, CMB, radiation discovered in 1965, which is considered the afterglow of the Big Bang. The CMB is a faint radiation that permeates the universe and is strong evidence that the universe once existed in an incredibly hot, dense state before expanding and cooling over billions of years. However, the findings of the JWST are forcing scientists to reassess certain aspects of the theory. For example, the discovery of galaxies that appear to have formed much earlier than previously thought challenges the idea that galaxies should have only started forming after a certain period following the Big Bang. The telescope's images show galaxies that seem to be larger and more developed than expected, especially at redshifts greater than 10, suggesting that these galaxies could have formed much earlier than the theory predicted. These discrepancies have led some scientists to propose alternative models of the universe's origin, such as the cyclic universe model, which suggests that the universe undergoes an infinite series of expansions and contractions. While these new theories present their own challenges, they offer intriguing possibilities for explaining the unexpected findings of the JWST. The James Webb Space Telescope. A new window to the universe. The James Webb Space Telescope, JWST, launched on December 25, 2021, is the most powerful space telescope ever built, serving as a successor to the Hubble Space Telescope. Unlike Hubble, which primarily captures visible and ultraviolet light, JWST is optimized for infrared observations. This is a key difference because infrared light can pass through dust clouds that obscure much of the visible light in space, allowing JWST to peer into regions of the universe that were previously hidden from view. JWST's resolution and sensitivity are far superior to anything that has come before. Its advanced optics and instruments are designed to study the formation of galaxies, stars, and planetary systems in unparalleled detail. With this in mind, the telescope is able to observe galaxies at distances so great that their light has taken billions of years to reach Earth, effectively looking back in time. One of JWST's major goals is to study the epoch of reionization, a period in the early universe that occurred around 400 million years after the Big Bang. During this time, the first stars and galaxies formed, and the universe began to transition from being opaque to transparent as light from these stars ionized the surrounding hydrogen gas. By observing this epoch, JWST can provide crucial information about the conditions that led to the formation of the first galaxies, and more importantly offer clues about how the early universe evolved into the structured and complex universe we observe today. The cyclic universe model. Possible. Given the unexpected findings of the JWST, some cosmologists are beginning to reconsider alternative models to the Big Bang theory. One such model is the cyclic universe theory, which suggests that the universe undergoes an infinite series of expansions and contractions. According to this theory, the universe doesn't have a singular beginning or end, but instead continually cycles through phases of expansion and collapse. The cyclic universe theory has gained attention due to its potential to address some of the contradictions in the Big Bang model, particularly the challenges posed by the discovery of galaxies that seem to have formed earlier than expected. If the universe has undergone previous cycles of expansion and contraction, it's possible that some of these early galaxies were the remnants of a previous cosmic era, not necessarily formed from the Big Bang itself. While this idea is still speculative and faces several challenges of its own, it offers an intriguing alternative to the Big Bang theory. The cyclic model could provide a new perspective on how galaxies, stars, and other structures could have emerged in the early universe, and it may help explain the unexpected findings from JWST. The James Webb Space Telescope has provided a wealth of new data that is reshaping our understanding of the universe's history. While the Big Bang theory remains a strong and well-supported model, these new discoveries challenge some of its key assumptions. As scientists continue to analyze the data from the JWST, they may be forced to revise our cosmic history and consider new theories to explain the unexpected complexities of the early universe. This ongoing research exemplifies the dynamic nature of scientific inquiry, where new evidence constantly pushes the boundaries of our knowledge and understanding. The discoveries from the James Webb Space Telescope, JWST, are not just a challenge to the Big Bang theory, they also open new avenues for understanding the universe's development, the formation of galaxies, and the overall nature of cosmology. The unexpected findings from the JWST raise several critical questions about the formation and evolution of galaxies, the nature of dark matter and dark energy, and the validity of the Big Bang theory as the ultimate explanation of the universe's origins. Scientists are now exploring new theoretical frameworks to account for these observations. The role of dark matter in early galaxy. Dark matter is believed to play a crucial role in galaxy formation by providing the gravitational scaffolding that allows ordinary matter to clump together and form stars and galaxies. However, JWST's discovery of well-formed galaxies at unexpectedly early times suggests that dark matter may have influenced galaxy formation in ways we do not fully understand. Some researchers propose that dark matter may have interacted differently in the early universe than it does today, possibly forming dense halos that accelerated the growth of galaxies. If true, this would require modifications to our current dark matter models. Could there be a pre-Big Bang era? The cyclic universe model suggests that the universe undergoes endless cycles of expansion and contraction rather than originating from a single Big Bang. This model, if validated, would imply that what we perceive as the Big Bang was merely the latest in a series of cosmic rebirths. One version of this theory, known as the ekpyrotic model, suggests that our universe arose from the collision of higher-dimensional branes in a multidimensional space. This model not only avoids the singularity problem of the Big Bang theory, but also provides an explanation for cosmic inflation without requiring an unexplained period of superluminal expansion. Modifying the inflationary model. While the Big Bang theory includes the concept of cosmic inflation, the JWST's findings suggest that our current inflationary models may be incomplete. Some cosmologists are exploring variations of inflation, such as supercooled inflation, which proposes that the early universe expanded more gradually than expected, allowing galaxies to form earlier. Multiverse inflation, which suggests that our universe is one of many parallel universes, each with different physical properties. These ideas remain speculative, but they are actively being explored as alternatives to the standard Big Bang model. One of the strongest pieces of evidence for the Big Bang theory is the redshift of galaxies, which suggests that the universe is expanding. However, some researchers have proposed alternative explanations, such as tired light hypothesis, the idea that light from distant galaxies loses energy due to interactions with cosmic dust or other particles rather than due to space expansion. Variable speed of light, VSL, theory. Some physicists suggest that the speed of light may have been different in the early universe, affecting how we interpret cosmic distances and expansion rates. Although these ideas remain controversial, they are being reconsidered in light of the JWSTs. The JWST has already transformed our understanding of the early universe, but it is only the beginning. Future telescopes and missions will provide even deeper insights. Next-generation telescopes. Nancy Grace Roman Space Telescope, NGRST. Scheduled for launch in the late 2020s, this telescope will study dark-energy exoplanets and galaxy formation with a wider field of view than JWST. 30-meter telescope, TMT, and extremely large telescope, ELT, ground-based telescopes with unprecedented resolution capable of detecting faint distant galaxies and studying the chemical composition of early stars. Advancements in cosmological simulations. Scientists are developing new computer simulations that incorporate JWST's findings to refine our models of galaxy formation. These simulations will help test theories like alternative inflation models, the cyclic universe, and modified dark matter interactions. Searching for primordial black holes. Some researchers speculate that JWST's observations might be detecting signatures of primordial black holes which could have formed shortly after the Big Bang and played a role in early galaxy formation. If these black holes exist, they could help explain the unexpectedly mature galaxies seen by JWST.